Tonight, we're going to witness something that happens in less than a single second, yet releases more energy than our sun will produce in its entire 10 billion year lifetime. A supernova. You've probably heard the word before. You might picture a star simply blowing up. But here's what almost nobody understands. A supernova isn't just an explosion. It's a catastrophic failure of physics itself inside the star's core. In the final moments, the core collapses so violently that matter is crushed beyond anything you've ever imagined. And the temperatures reach hundreds of billions of degrees. What triggers this? What actually happens in those last fractions of a second? And why does the universe need this destruction to exist the way it does? By the end of tonight, you're going to understand exactly what happens when a star dies. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what happens during a supernova, you first need to understand what a star actually is. Not in the poetic sense, not a twinkling light in the sky. You need to understand what's happening inside a star right now, at this very moment. Because a star is not a static object. It's not a ball of fire sitting quietly in space. A star is a war. A constant, relentless war between two of the most powerful forces in the universe, and a supernova is what happens when one side finally wins. On one side, you have gravity. Gravity is always trying to crush the star. Always. Every single moment of a star's existence, gravity is pulling every atom of that star toward the center. The star has mass, enormous amounts of mass, and all that mass creates a gravitational pull that wants to compress everything inward. If gravity were the only force at work, the star would collapse into a tiny, incredibly dense point, almost instantly. The sun, for example, has a mass of about 1.99 times 10 to the 30th kilograms. That's roughly 333,000 times the mass of Earth. All of that mass is pulling inward, trying to shrink the sun down to the smallest possible size. Gravity never stops. It never takes a break. It never weakens from the inside. It's always there, always pressing, always trying to win. On the other side, you have pressure. Specifically, radiation pressure and thermal pressure generated by nuclear fusion in the star's core. Deep inside the star, the temperatures and pressures are so extreme that atoms are stripped of their electrons. The core becomes a sea of naked atomic nuclei and free electrons, a state of matter called plasma. And in that plasma, at temperatures of millions or even billions of degrees, something extraordinary happens. Atomic nuclei are smashed together with such force that they fuse, combining into heavier elements. This process, nuclear fusion, releases energy. Enormous amounts of energy. That energy heats the surrounding material, creating outward pressure that pushes against gravity's inward pull. This is the war. Gravity pulling in, fusion pushing out. And for most of a star's life, these two forces are in near perfect balance. The star doesn't collapse because fusion pushes back. The star doesn't fly apart because gravity holds it together. This balance is called hydrostatic equilibrium, and it's one of the most important concepts in all of stellar physics. Every stable star you see in the night sky, every single one, is in this state of balance. The sun has been in hydrostatic equilibrium for about 4.5 billion years. It will remain in this state for roughly another 5 billion years. During all that time, gravity and fusion pressure are locked in a stalemate. Neither side gains a decisive advantage. The star sits there, shining steadily, century after century, millennium after millennium, converting fuel into energy and balancing itself against its own weight. But here's the critical thing you need to understand. This balance depends entirely on the star having fuel to burn. As long as there's fuel in the core, fusion continues, energy flows outward, pressure holds gravity at bay. If the fuel runs out, the pressure drops. And when the pressure drops, gravity wins. There's nothing else to stop it. No backup system, no emergency brake. Gravity simply takes over and the star begins to collapse. That's the fundamental truth behind every supernova. It's not that the star explodes for some random reason. It's that the star runs out of ways to fight gravity, and gravity does what gravity has always been trying to do. It crushes everything. Now, not every star dies as a supernova. The type of death a star experiences depends almost entirely on one thing: its mass. Our Sun is what astronomers call a main sequence star, specifically a G-type yellow dwarf. It has a modest mass by stellar standards. When the Sun eventually runs out of hydrogen fuel in its core, it will swell into a red giant, shed its outer layers, and leave behind a small, dense remnant called a white dwarf. No explosion, no supernova. Just a slow, quiet fading over billions of years. The Sun simply doesn't have enough mass to generate the conditions necessary for a supernova. But some stars are much more massive than the Sun. 8 times more massive. 10 times. 20 times. Some are 50 or even 100 times the mass of the Sun. These are the stars that end their lives in supernovae. And the reason is that their greater mass creates greater gravitational pressure on the core, which in turn requires higher temperatures and pressures to maintain hydrostatic equilibrium. This drives fusion to extremes that smaller stars can never reach. And it's in these extremes that the seeds of catastrophe are planted. Let's follow the life of one of these massive stars. Let's say it's about 20 times the mass of the Sun. A blue supergiant, blazing with a luminosity tens of thousands of times greater than our Sun. On the surface, it looks like a brilliant blue-white beacon. But inside, deep in its core, a complex and accelerating drama is unfolding. When the star first ignites, it does what all stars do. It fuses hydrogen into helium. 4 hydrogen nuclei, which are just protons, are combined to form one helium nucleus, which contains 2 protons and 2 neutrons. In the process, a tiny amount of mass is converted directly into energy, according to Einstein's famous equation, E equals mc squared. The amount of mass lost is small, only about 0.7% of the original hydrogen mass. But when you're converting millions of tons of hydrogen every second, that tiny percentage adds up to a staggering amount of energy. The Sun, for example, converts about 600 million tons of hydrogen into helium every single second, and it releases energy equivalent to about 3.8 times 10 to the 26th watts. That's 380 trillion watts every second. And it's been doing this for 4.5 billion years. A star 20 times the mass of the Sun burns through its hydrogen fuel much faster. You might think a bigger star would last longer because it has more fuel. But the opposite is true. More massive stars burn hotter, which means they consume their fuel at a dramatically higher rate. The relationship isn't linear either. A star with twice the mass doesn't just burn twice as fast, it burns roughly 8 to 10 times faster. The luminosity of a star scales roughly as the cube, or even the 4th power of its mass. So a star with 20 times the sun's mass doesn't shine 20 times brighter. It shines tens of thousands of times brighter. That means it's consuming its hydrogen tens of thousands of times faster. While the sun will spend about 10 billion years fusing hydrogen, a star with 20 solar masses will exhaust its core hydrogen in only about 10 million years. That sounds like a long time, but in cosmic terms, it's almost nothing. The sun's lifetime is 1,000 times longer. Massive stars live fast and die young. They blaze with incredible brilliance, outshining entire collections of smaller stars, but they pay for that brilliance with drastically shortened lives. When the hydrogen in the core is finally exhausted, something important happens. Fusion stops in the core. Without the outward pressure from hydrogen fusion, the core begins to contract under gravity. As it contracts, it heats up. The material surrounding the now helium core still contains hydrogen, and the heat from the contracting core ignites hydrogen fusion in a shell around the core. Meanwhile, the core itself keeps contracting and heating until it reaches a temperature of about 100 million degrees. At this temperature, something new becomes possible: helium fusion. Helium fusion is a different process from hydrogen fusion. It's called the triple alpha process because it involves combining 3 helium-4 nuclei, also called alpha particles, to form one carbon-12 nucleus. This process requires much higher temperatures than hydrogen fusion because helium nuclei have 2 protons each, meaning they carry a stronger positive electrical charge. Since charges repel each other, you need enormous temperatures to give the nuclei enough kinetic energy to overcome this repulsion and get close enough for the strong nuclear force to bind them together. The triple alpha process is actually a 2-step reaction. First, 2 helium nuclei fuse to form beryllium-8. But beryllium-8 is extremely unstable. It exists for only about 10 to the negative 16th seconds before it decays back into 2 helium nuclei. That's less than 1/10 of a quadrillionth of a second. In that impossibly brief window, a 3rd helium nucleus must collide with the beryllium-8 and fuse with it to form carbon-12. The odds of this happening in any single interaction are incredibly small. But in the core of a star, where trillions upon trillions of helium nuclei are smashing into each other every fraction of a second, it happens often enough to sustain fusion and produce significant amounts of carbon. Some of that carbon then captures another helium nucleus to form oxygen-16. So helium burning produces both carbon and oxygen, 2 of the most important elements for life as we know it. The carbon in your body, the oxygen you're breathing right now, these elements were forged in the cores of stars through this exact process, the triple alpha process followed by alpha capture. Now, here's where things start to accelerate. Helium fusion produces less energy per reaction than hydrogen fusion. This means the star needs to burn helium faster to maintain the same outward pressure against gravity. A massive star will burn through its core helium in roughly 1 million years. That's 1/10 of the time it spent burning hydrogen. The clock is already speeding up. When the helium in the core is exhausted, the same thing happens again. Fusion stops. The core contracts. It heats up. And at about 600 million degrees, a new fuel ignites. Carbon. Carbon nuclei begin to fuse, producing a variety of products including neon, sodium, and magnesium. Carbon burning requires even higher temperatures because carbon nuclei have 6 protons each. The electrostatic repulsion is much stronger. You need far more energy to force them together. And carbon burning is even faster than helium burning. In a star of 20 solar masses, carbon burning in the core lasts only about 1,000 years. We've gone from 10 million years of hydrogen burning to 1 million years of helium burning to 1,000 years of carbon burning. Each stage is shorter than the last by roughly a factor of 1,000. The star is accelerating toward its own destruction, and each new phase of fusion burns faster and hotter than the one before. When carbon is exhausted, the core contracts again and heats up further. At about 1.2 billion degrees, neon begins to fuse. Neon burning is unusual because it actually begins with photodisintegration, a process where high-energy photons, gamma rays, shatter neon nuclei, breaking them into oxygen and helium. The freed helium nuclei then fuse with the remaining neon to form magnesium. Neon burning lasts only about a few years. Just a few years. The star has gone from millions of years of stable burning to a phase that lasts shorter than a presidential term. After neon, the core contracts again. At about 1.5 billion degrees, oxygen fusion ignites. Oxygen nuclei with 8 protons each require tremendous energy to overcome their mutual repulsion. When they fuse, they primarily produce silicon-28, along with sulfur and other elements. Oxygen burning lasts about 6 months to a year, half a year. The acceleration is breathtaking. Each successive fuel burns at higher temperatures, produces less energy per reaction, and is exhausted faster. And then we arrive at the final stage, the last stand, silicon burning. When the oxygen fuel is exhausted and the core contracts once more, temperatures reach roughly 3 billion degrees. At this point, silicon nuclei begin to fuse, but silicon burning is not a simple process like hydrogen or helium fusion. Silicon has 14 protons. The electrostatic barrier is enormous. What actually happens is a complex series of reactions involving photodisintegration and alpha captures. High-energy photons break silicon nuclei apart, releasing alpha particles, which are then captured by other silicon nuclei, building up heavier elements step by step. Silicon to sulfur, sulfur to argon, argon to calcium, calcium to titanium, titanium to chromium, chromium to iron. Each step adds 2 protons and 2 neutrons. Each step moves up the periodic table. And each step happens faster than the last because the temperatures are so extreme that the reaction rates are enormous. Silicon burning lasts about 1 day. In some models, as little as a few hours. 1 day. Let me put this in perspective. The star spent 10 million years burning hydrogen, 1 million years burning helium, 1,000 years burning carbon, a few years burning neon, less than a year burning oxygen, and now 1 single day burning silicon. The entire trajectory of the star's life has been leading to this point, accelerating relentlessly, each phase shorter and more desperate than the last. The star is running out of options, and it's running out of them fast. What silicon burning produces is iron. Specifically, iron 56, along with some nickel 56, which later decays into iron. And iron is where everything changes. Iron is the end of the line, the final stop, the point of no return. To understand why iron is so special, you need to understand something about nuclear binding energy. Every atomic nucleus is held together by the strong nuclear force. The strength of this binding varies depending on the element. For lighter elements, from hydrogen up through iron, each step of fusion releases energy because the product nucleus is more tightly bound than the reactants. The nuclei become more stable, and the excess energy is released. This is why fusion works as an energy source. You start with loosely bound nuclei, fuse them into more tightly bound nuclei, and pocket the energy difference. But iron 56 sits at the peak of the binding energy curve. It is the most tightly bound nucleus in nature. There is no element you can fuse iron into that would be more stable. Any fusion reaction involving iron doesn't release energy. It consumes energy. It's endothermic rather than exothermic. Fusing iron doesn't push outward against gravity. It would actually steal energy from the star, accelerating its collapse rather than preventing it. This is a death sentence for the star. For millions of years, the star has been fighting gravity by fusing lighter elements into heavier ones, releasing energy at each step. But now it's produced an element that can't be fused profitably. The star has built an iron core, and that iron core is a ticking bomb. Not because iron is explosive, but because iron is the one thing the star cannot use as fuel. Think of it like this. Imagine you're heating your house by burning wood. You start with easy burning kindling. Then you move to larger logs. Then you start burning furniture. Then floorboards. Then the walls themselves. Each fuel burns faster and provides less heat than the last, but it keeps the house warm. Now imagine you've burned everything except the foundation. The foundation is made of stone. You can't burn stone. No matter how hot you make it, stone won't combust. It won't release heat. It just sits there. The fire goes out. And without the heat, the house succumbs to the cold. That's what iron is to a star. It's the stone foundation. The fuel that isn't fuel. The end of the road. As silicon burning proceeds in the core, iron accumulates. The iron core grows, getting heavier and heavier. At this point, the star has developed a layered structure that astronomers often compare to an onion. If you could slice the star open and look at a cross-section, you'd see distinct layers, each containing different elements. The outermost layer is hydrogen, the original material of the star that never got hot enough to fuse. Below that is a shell of helium. Below that, a shell of carbon and oxygen. Then neon and magnesium. Then oxygen and silicon. Then silicon and sulfur. And at the very center, the iron core. Each of these layers is actively fusing, creating the next heavier element and sending energy outward. It's like a series of nested furnaces, each burning a different fuel. But the energy output decreases as you go deeper. The innermost shells burn the most furiously, but produce the least energy per unit of fuel. The whole structure is barely holding itself together, maintained by a precarious balance that's growing more fragile by the hour. If you could somehow see this structure from the inside, you'd witness a star within a star within a star, each layer hotter and denser than the one above it, each one fusing material at rates that would seem impossible by human standards. The temperatures increase dramatically as you move inward. The outermost hydrogen layer might be at a few million degrees. The helium shell is at perhaps 100 million degrees. The carbon-burning shell is at 600 million degrees. And the silicon-burning shell surrounding the iron core is at over 3 billion degrees. Each layer is its own thermonuclear furnace, and together they form one of the most complex energy-producing structures in the cosmos. The iron core itself is supported not by fusion, but by electron degeneracy pressure. This is a quantum mechanical effect. Electrons obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state in the same location. When matter is compressed to extreme densities, the electrons are squeezed into higher and higher energy states. They resist further compression, creating a pressure that doesn't depend on temperature, but on density. This is the same force that supports white dwarfs. the dense remnants of low-mass stars that have exhausted their fuel. But electron degeneracy pressure has a limit. It can only support a core up to a certain mass, about 1.4 times the mass of the Sun. This is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930 when he was just 19 years old, working out the mathematics during a sea voyage from India to England. It was a brilliant piece of theoretical physics, one that would eventually earn him the Nobel Prize in 1983. The implication of his calculation was profound. If the core's mass exceeds this limit, electron degeneracy pressure simply isn't strong enough to hold it up against gravity. There is a maximum weight that this quantum mechanical force can bear, and once you exceed it, nothing stops the collapse. And here's the problem. As silicon burning continues in the shell around the iron core, it keeps adding more iron to the core. The core grows heavier. It gets closer and closer to the Chandrasekhar limit. And all the while, the temperature in the core is climbing. At temperatures above about 5 billion degrees, photodisintegration becomes significant. High-energy gamma-ray photons begin to shatter iron nuclei, breaking them apart into helium nuclei and individual neutrons. This process absorbs enormous amounts of energy. Energy that was supporting the core against gravity is suddenly consumed. It's like pulling the supports out from under a bridge. The core's ability to hold itself up weakens dramatically. At the same time, another process accelerates the crisis. At these extreme temperatures and densities, electrons are captured by protons in a process called electron capture or inverse beta decay. The electron combines with the proton to form a neutron and a neutrino. The neutrino escapes, carrying energy away from the core, and crucially removing electrons removes electron degeneracy pressure. The very force that was holding the core up is being systematically dismantled. The core is now in catastrophic trouble. It's losing pressure support from two directions simultaneously. Photodisintegration is consuming thermal energy. Electron capture is removing the electrons that provide degeneracy pressure. Gravity, which has been waiting patiently for billions of years, finally gains the upper hand. The iron core begins to collapse. This is the moment everything changes. For millions of years, the star maintained its balance. It burned through fuel after fuel, each one buying a little more time. Hydrogen gave it millions of years. Helium gave it 1 million more. Carbon gave it centuries. Neon gave it years. Oxygen gave it months. Silicon gave it hours. And now, it's out of time. The iron core has crossed the Chandrasekhar limit. Electron degeneracy pressure has failed. Photodisintegration is sapping the core's energy. And gravity, relentless and patient, does what it has always been trying to do. The core begins to fall inward. Not slowly, not gradually. It accelerates. Within milliseconds, the inner core will be collapsing at a significant fraction of the speed of light. What happens next is one of the most violent events in the known universe. In less than a second, more energy will be released than the star produced in its entire multi-million year lifetime. But right now, in this precise moment, the star still looks perfectly normal from the outside. The surface is still shining. The outer layers have no idea what's happening deep in the core. Light and information travel at finite speeds, and the core is buried beneath trillions of tons of stellar material. The surface of the star might continue to shine peacefully for hours after the core has already begun its fatal collapse. If you were watching this star through a telescope at this exact moment, you would see nothing unusual. Just a bright blue supergiant, steady and calm, giving no hint of the catastrophe unfolding in its heart. An observer standing on a planet orbiting this star would see a normal sky, normal light, normal warmth. They would have no warning, no indication whatsoever that deep beneath the surface, in a region smaller than the Earth, the core of their star had just crossed a threshold from which there is no return. The star looks alive, but its core is already dead. The iron has accumulated. The fuel is spent. The balance is broken, and gravity has won. What happens next, in the fraction of a second after the core begins its collapse, is one of the most extraordinary events in all of physics. That collapse, that implosion, the rebound, the flood of neutrinos, the stalled shock wave and its revival, all of that involves physics stranger and more violent than almost anything else the universe has to offer. The temperatures will reach hundreds of billions of degrees. The densities will exceed anything found anywhere else in the cosmos, except inside black holes. And in the middle of all that chaos, something remarkable will happen. The star will bounce. And from that bounce, from that moment of recoil, a supernova is born. But we're getting ahead of ourselves. For now, understand this. The star you've been watching, this massive, brilliant, seemingly invincible blue supergiant, has been fighting a losing battle since the moment it was born. Every phase of fusion was just a temporary reprieve. Every new fuel bought a little more time, but less time than the fuel before it. The star was always going to reach iron. It was always going to run out of options, and gravity was always going to win. The story of a massive star is the story of a countdown. It starts slow and accelerates, faster and faster, until in the final hours, minutes, and seconds, everything happens at once. 10 million years of hydrogen burning, 1 million years of helium burning, 1,000 years of carbon burning, a few years of neon burning, less than a year of oxygen burning, a single day of silicon burning, and then, in less than 1 second, the core collapses. The entire life of the star has been building toward this one moment, and that moment is almost here. The iron core has been growing for hours. Silicon burning in the shell above it has been steadily adding mass, layer by layer, like sand piling onto a table that's already bending under the weight. The core is now roughly the size of Earth, about 8,000 miles across, but it contains roughly 1.5 times the mass of the entire Sun. The density at the center is already staggering, around 100 billion kilograms per cubic meter. For comparison, the densest material you encounter in everyday life, something like lead or gold, has a density of about 10,000 to 20,000 kilograms per cubic meter. The iron core is millions of times denser than anything on Earth, and it's about to get incomprehensibly denser. The temperature in the core has climbed past 10 billion degrees. At this extreme, photons carry so much energy that they begin tearing iron nuclei apart. This is photodisintegration, and it's devastating. Each iron nucleus that gets shattered absorbs energy, a tremendous amount of energy. The destruction of a single iron nucleus into 13 helium nuclei and 4 neutrons absorbs about 124 million electron volts. That might not sound like much, but when trillions upon trillions of iron nuclei are being shattered every microsecond, the total energy drain is colossal. In a matter of milliseconds, photodisintegration absorbs the equivalent of all the energy the star produced over hundreds of thousands of years of nuclear burning. It's like opening a drain at the bottom of a bathtub. The thermal energy that was helping support the core against gravity is suddenly pouring away. Simultaneously, electron capture is accelerating. At these densities, electrons are being forced into protons, converting them into neutrons and producing neutrinos. Each electron that disappears removes a tiny bit of electron degeneracy pressure, and each neutrino that's created carries energy away from the core. At first, the neutrinos escape freely. They're ghostly particles that barely interact with matter. Under normal conditions, a neutrino can pass through a light year of solid lead without hitting a single atom. They stream out of the core at nearly the speed of light, carrying energy with them. The core is hemorrhaging energy from every direction. Photodisintegration drains thermal energy. Electron capture removes degeneracy pressure. Neutrinos carry energy away entirely. It's a triple assault on the core's ability to support itself. And gravity, patient and relentless, has been waiting for exactly this moment. The collapse begins. Not gradually, not gently. The inner core, roughly the innermost portion containing about 0.6 to 0.8 solar masses, begins to fall inward. Within milliseconds, the collapse accelerates to roughly 70,000 kilometers per second. That's about 23% of the speed of light. Nearly a quarter the fastest speed anything can travel in the universe. Think about that. A region the size of Earth, containing more mass than the Sun, is imploding at a quarter of the speed of light. The violence of this is almost beyond description. The outer core follows, falling inward slightly behind the inner core. Material from the layers above begins to rain down as well. The entire central region of the star is in freefall. Not orbiting, not drifting. Free falling, accelerating under gravity with nothing to slow it down. The collapse is so fast that it's essentially happening in real time. The inner core goes from the size of Earth to the size of a city in less than 1 second. Actually, in less than 1/10 of a second. In roughly 300 milliseconds, maybe less, the inner core collapses from a diameter of about 8,000 kilometers to a diameter of roughly 30 kilometers. That's a compression factor of more than 250 in diameter. In volume, the compression is more than 15 million to 1. Material that was spread across an Earth-sized sphere is now packed into a ball, the size of a large metropolitan area. During this collapse, the density skyrockets. The core density goes from around 100 billion kilograms per cubic meter to over 100 trillion kilograms per cubic meter. And then it keeps climbing. As the collapse continues and the inner core gets smaller and smaller, the density reaches levels found nowhere else in the universe except inside neutron stars and black holes. At peak compression, the density reaches somewhere around 200 to 300 quadrillion kilograms per cubic meter. At this density, a teaspoon of the material would weigh roughly 1 billion tons. More than every building, every car, every ship, every structure ever built by humanity combined, packed into a volume smaller than a sugar cube. At these densities, something extraordinary happens. Matter reaches nuclear density. The individual neutrons and protons in the collapsing core are squeezed so tightly together that they're essentially touching. There's no space between them. The core has become a single enormous atomic nucleus, roughly 30 kilometers across. And at nuclear density, a new force comes into play. The strong nuclear force, which normally operates only over distances smaller than an atomic nucleus, now becomes relevant across the entire inner core. And the strong nuclear force at very short distances is repulsive. When you try to squeeze nuclear matter beyond nuclear density, the strong force pushes back hard. This is the moment of core bounce. The inner core, which has been collapsing at a significant fraction of the speed of light, suddenly encounters this wall of nuclear repulsion. The collapse doesn't slow gradually, it stops almost instantaneously. The inner core goes from falling inward at 70,000 kilometers per second to a dead stop in less than a millisecond. The deceleration is violent beyond anything else in the known universe, and just like a ball bouncing off a hard floor, the inner core rebounds. It doesn't just stop, it bounces back outward. This bounce sends a powerful pressure wave rippling outward through the still infalling material of the outer core. This pressure wave steepens almost immediately into a shock wave. A shock wave is different from a regular pressure wave because it moves faster than the speed of sound in the material, creating an abrupt discontinuity. On one side of the shock, material is falling inward. On the other side, material is being pushed outward. The shock propagates outward through the still collapsing outer core like a wall of force, slamming into the infalling material and trying to reverse its direction. If this shock wave could simply plow through the entire star and blow it apart, you'd have your supernova. Clean, simple, and straightforward. Core collapses, bounces, shock wave races outward, and detonates the star. This was what early models of supernova proposed. It was called the prompt shock mechanism, and for a while, physicists thought this was how supernovae worked. But there's a problem. A serious one. The shock wave stalls. It doesn't make it through. Here's why. As the shock wave moves outward through the outer core, it runs into material that's still falling inward at enormous speed. The shock has to not only stop this material but reverse its direction, pushing it outward. This costs energy. An enormous amount of energy. Every gram of infalling material that the shock encounters saps its strength. But that's not the worst part. The worst part is photodisintegration again. Remember how gamma rays were tearing apart iron nuclei in the core? The same thing happens at the shock front. The shock heats the material it passes through to extremely high temperatures. And at those temperatures, the iron and silicon nuclei in the infalling material are blasted apart into helium nuclei, protons, and neutrons. Each nucleus that gets shattered absorbs energy from the shock, and there is a lot of material falling in. The outer core contains several tenths of a solar mass of iron and silicon, all of which the shock has to fight through. The numbers are devastating. The energy absorbed by photodisintegration behind the shock is enormous, on the order of 10 to the 51 ergs per tenth of a solar mass of material that the shock crosses. The shock was born with roughly 10 to the 51 ergs of kinetic energy from the core bounce, which sounds like a lot, but it's barely enough to dissociate even a small fraction of the infalling material. Within about 10 to 20 milliseconds after the bounce, the shock wave has lost most of its energy. It slows down. It stalls. It sits there, roughly 100 to 200 kilometers from the center of the newly formed proto-neutron star, no longer advancing. The infalling material continues to pile up on top of it, pushing it back, compressing it. The shock has stalled, and the supernova appears to have failed. This was one of the greatest puzzles in astrophysics for decades. computer simulations consistently showed the same result. The shock stalls. Every time. If the shock can't break through, the star doesn't explode. Instead, the material just keeps falling onto the proto-neutron star, adding mass until eventually the whole thing collapses into a black hole. No supernova, no explosion, no scattering of heavy elements into space, just a star that quietly disappears, leaving behind a black hole. But we know supernovae happen. We observe them. We see the expanding remnants. We detect the light, the neutrinos, the gravitational waves. Something must revive the stalled shock. Something must inject enough energy to push it through the rest of the star. For years, physicists struggled with this question. What saves the supernova? The answer, as best we understand it today, comes from the most elusive particles in the universe, neutrinos. During the collapse and bounce, the proto-neutron star at the center is unimaginably hot. Its temperature exceeds 100 billion degrees. At these temperatures, it radiates neutrinos in astonishing quantities. The total energy released in neutrinos during a core collapse supernova is roughly 3 times 10 to the 53 ergs. To put that in perspective, the kinetic energy of the explosion, the actual blast that tears the star apart, represents only about 1% of the total energy released. The visible light from a supernova, which is itself extraordinarily bright, temporarily outshining an entire galaxy of hundreds of billions of stars, represents a tiny fraction even of that, less than 1/100th of 1%. The remaining roughly 99% of the total energy comes out as neutrinos. A supernova is, fundamentally, a neutrino event. The light show that we observe is just a tiny side effect. These neutrinos are produced in the proto-neutron star and radiate outward in all directions. Now, under normal circumstances, neutrinos barely interact with matter. They would pass right through the outer layers of the star without transferring any energy. But conditions behind the stalled shock are not normal. The densities there are still extremely high, much higher than ordinary matter. And at these densities, even neutrinos, which are famously reluctant to interact with anything, have a small but meaningful chance of being absorbed by the neutrons and protons in the material behind the shock. When a neutrino is absorbed by a neutron, it converts the neutron back into a proton and an electron, releasing energy in the process. When a neutrino is absorbed by a proton, it converts it into a neutron and a positron, also releasing energy. These absorption events deposit energy behind the stalled shock. Not much energy per individual neutrino, but the number of neutrinos streaming outward from the proto-neutron star is absolutely staggering. Roughly 10 to the 58 neutrinos are emitted in just the first few seconds. That's a number so large it defies comprehension. If even a tiny fraction of those neutrinos, say 5 to 10%, deposit their energy in the region behind the shock, it's enough. The energy transferred to the material behind the shock heats it up, increasing its pressure and gradually pushes the shock outward. This is called the neutrino-driven mechanism, and it's currently the leading theory for how most core collapse supernovae actually explode. The neutrinos don't do it instantly. It takes time, hundreds of milliseconds, maybe even a full second or more. The shock sits there, stalled, while neutrinos gradually deposit energy behind it. The region behind the shock heats up. The pressure builds, and eventually, the shock is revived. It begins to move outward again, slowly at first, then faster and faster as it encounters less and less resistance. But there's more to the story. The neutrino-driven mechanism alone, at least in simple, one-dimensional computer models, still struggles to produce explosions. When you simulate the collapse in one dimension, treating the star as a perfect sphere with everything happening symmetrically, the neutrino heating often isn't quite enough. The shock revives weakly or not at all. This puzzled astrophysicists for years. The physics seemed right. Neutrino heating should work. But the simulations kept failing. The breakthrough came when scientists began running simulations in 2 and then 3 dimensions. When you allow the collapsing material to be asymmetric, to develop bumps and swirls and turbulent motions, everything changes. In multi-dimensional simulations, 2 crucial phenomena emerge that help the supernova succeed: convection and the standing accretion shock instability, or SASI. Convection is something you're already familiar with in everyday life. When you heat water in a pot, the hot water at the bottom rises and the cooler water at the top sinks, creating circulating currents. The same thing happens behind the stalled shock in a collapsing star. The material closest to the proto-neutron star gets heated by neutrinos and becomes buoyant. It rises outward. Cooler material farther from the neutron star sinks inward, gets heated in turn, and rises again. This convective churning does something incredibly important. It takes hot material from near the neutron star, where the neutrino heating is strongest, and brings it up to the shock front. And it takes cooler material from near the shock, and brings it down to the heating region, where it can absorb more neutrino energy. Convection acts like a conveyor belt, efficiently transporting energy from the neutrino heating region to the shock. Without convection, the heated material just sits behind the shock, gradually losing energy through radiation. With convection, it's constantly being refreshed. Hot material rises to push on the shock. Cool material descends to get heated. The whole system becomes much more efficient at converting neutrino energy into outward pressure. SASI is even more dramatic. The standing accretion shock instability is a large-scale sloshing motion of the entire shock front. Instead of remaining a perfect sphere, the shock begins to oscillate. It bulges outward on one side while retreating on the other. This sloshing grows over time, becoming more and more violent. The shock wobbles back and forth like a water balloon being shaken. SASI amplifies turbulence behind the shock and creates large-scale asymmetries in the flow. These asymmetries are crucial because they allow the shock to expand preferentially in certain directions. Instead of trying to push outward uniformly against the infalling material, the shock can break through in one direction while material continues to fall in from other directions. It's like trying to push open a heavy door. If you push uniformly across the entire surface, it's difficult. But if you concentrate your force on one edge, the door swings open. SASI helps the shock find the path of least resistance. Together, convection and SASI transform the dynamics behind the stalled shock. They increase the efficiency of neutrino heating. They create turbulent pressure that adds to the thermal pressure behind the shock, and they introduce asymmetries that help the shock break through. In modern 3-dimensional simulations running on the most powerful supercomputers in the world, these effects consistently produce successful explosions. The shock is revived, it accelerates outward through the star, and the supernova proceeds. The simulations aren't perfect. There are still uncertainties in the physics, particularly in how neutrinos interact with the dense nuclear matter in the proto-neutron star. But the broad picture is now well established. Neutrino heating, amplified by convection and SASI, is the engine that drives core collapse supernovae. The revival of the shock takes somewhere between a few hundred milliseconds and about 1 second after the bounce. Once revived, the shock accelerates outward through the star's outer layers. These layers are the shells of silicon, oxygen, neon, carbon, helium, and hydrogen that we talked about earlier, are still largely unaware of what's happened in the core. They've been sitting there, fusing away, minding their own business while the core collapsed and bounced below them. Now, a wall of energy comes screaming outward at tens of thousands of kilometers per second. The shock tears through these layers, heating them to billions of degrees, igniting explosive nuclear burning in the process. This explosive nucleosynthesis produces a burst of new elements as the shock passes through each layer. Silicon is fused into iron and nickel. Oxygen is fused into silicon and sulfur. Carbon is fused into oxygen and neon. The shock doesn't just blow the star apart, it cooks the material as it goes, forging new elements in the process. The entire outer envelope of the star is ejected outward. Billions upon billions of tons of material, several solar masses worth, are launched into space at speeds ranging from a few thousand to 30,000 or even 40,000 kilometers per second. That's roughly 10% of the speed of light. This expanding cloud of gas and newly forged elements is what we see as a supernova. The light comes primarily from the radioactive decay of nickel-56, which is produced in enormous quantities during the explosive burning. Nickel-56 decays into cobalt-56 with a half-life of about 6 days, and cobalt-56 decays into iron-56 with a half-life of about 77 days. These radioactive decays release gamma rays that heat the expanding debris from the inside, keeping it glowing for weeks and months after the initial explosion. This is why supernovae remain visible for so long. They're powered by the slow decay of radioactive nickel, not by the initial blast itself. Now, not all core collapse supernovae look the same. Astronomers classify them into several types based on what they observe in the light spectrum of the explosion. And these types tell us something important about the star that exploded. What specifically they tell us is what layers the star still had when it died. A Type 2 supernova shows strong hydrogen lines in its spectrum. This means the star still had its outer hydrogen envelope when it exploded. The shock wave had to blast through all those outer layers, including the hydrogen, and that hydrogen is visible in the light that we observe. These are the most straightforward core collapse supernovae. A massive star, still wrapped in its original hydrogen atmosphere, collapses and explodes. The progenitor is typically a red or blue supergiant that retained most of its mass throughout its life. But some massive stars lose their outer layers before they explode. Stars are not perfectly sealed containers. They have stellar winds, streams of particles flowing off their surfaces into space. For very massive stars, these winds can be extremely powerful. A star with 30 or 40 solar masses can lose several solar masses worth of material through its wind over the course of its lifetime. The most luminous and massive stars, called Wolf-Rayet stars, have winds so fierce that they strip away the star's entire hydrogen envelope, exposing the helium layer beneath. When one of these strip stars collapses and explodes, the resulting supernova has no hydrogen in its spectrum, because the hydrogen was blown away long before the explosion. This is a Type 1b supernova. It's still a core collapse event, the same iron core, the same collapse, the same bounce, the same neutrino-driven shock revival. but the star has lost its hydrogen coat. The light we see comes from the deeper layers. Take this one step further. Some stars lose not only their hydrogen envelope, but also most of their helium layer. Their winds are so powerful, or they have binary companions that gravitationally strip away their outer material, that by the time they explode, they've been peeled down to their carbon and oxygen layers. When these stars collapse and explode, the spectrum shows neither hydrogen nor helium. This is a type YC supernova. Same core collapse mechanism underneath, different outer packaging. The distinction between type 2, type 1b, and type 1c is not about how the core collapses. The core collapse is essentially the same in all three cases. The iron core grows past the Chandrasekhar limit, electron degeneracy pressure fails, the core implodes, bounces, the shock stalls, neutrinos revive it, and the star explodes. What differs is the state of the star's envelope. How much of its original material has it retained? How much has been stripped away by winds or binary interactions? The classification tells us about the life the star lived before it died, not about the mechanism of death itself. There are further subdivisions. Type 2, P supernovae, where the P stands for plateau, show a long period of roughly constant brightness lasting several months. This plateau occurs because the expanding hydrogen envelope remains opaque for an extended period, gradually releasing the energy deposited by the shock. As the hydrogen recombines, becoming transparent layer by layer from the outside in, the supernova maintains a roughly constant luminosity. Type 2 L supernovae, where the L stands for linear, show a more steady decline in brightness. This happens when the hydrogen envelope is thinner, so there's less material to sustain the plateau. Type 2 supernovae, where the N stands for narrow, show narrow emission lines caused by the shock wave plowing into dense material that the star shed before the explosion. The star lost mass heavily in the years or decades before exploding, creating a dense shell of gas around it. When the supernova shock hits this shell, it lights up, producing those characteristic narrow spectral lines. Each subtype tells a slightly different story about the dying star, its mass, its history of mass loss, its environment. But beneath all these variations, the engine is the same. An iron core that can no longer fight gravity, a collapse that reaches nuclear density, a bounce, a stalled shock, a flood of neutrinos, and finally, an explosion that tears the star apart from the inside out. Let me give you a sense of the energy involved, because the numbers are genuinely difficult to process. The total energy released in a core collapse supernova is approximately 3 × 10 to the 53 ergs. That's 3 × 10 to the 46 joules, if you prefer SI units. This is an almost inconceivable amount of energy. It's roughly equal to the total energy output of the Sun over its entire 10 billion year lifetime, released in a matter of seconds. Or, to put it another way, if you could somehow capture all the energy from a supernova and use it to power light bulbs, you could illuminate 10 trillion 100-watt light bulbs for an entire year. The explosion is so powerful that during its peak brightness, a single supernova can outshine its entire host galaxy. One star, brighter than hundreds of billions of stars combined. For a few weeks, the dying star becomes the brightest object in its galaxy, visible across tens of millions or even billions of light years. And yet, as I mentioned, roughly 99% of that energy isn't visible at all. It's carried away by neutrinos. The neutrino burst from a core collapse supernova. is one of the most extraordinary events in nature. In February of 1987, astronomers detected a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years away. This supernova, designated SN 1987A, was the closest supernova observed since Kepler's supernova in 1604. And for the first time in history, we detected the neutrinos from it. 25 neutrinos were captured by detectors on Earth, arriving a few hours before the visible light. Just 25 particles, out of the roughly 10 to the 58 neutrinos that the supernova released. The vast majority passed straight through the Earth without interacting with anything. The fact that we detected even 25 of them was extraordinary and confirmed the basic picture of core collapse that physicists had been developing for decades. The neutrinos arrived first because they were released during the core collapse itself, before the shockwave had time to break through the star's surface and produce visible light. This detection provided direct evidence that the core collapse occurs before the visible explosion, exactly as the theory predicted. What's left behind at the center of all this violence? The answer is the proto-neutron star. The inner core, which bounced and launched the shockwave, doesn't disappear. It remains at the center, a hot, dense, rapidly rotating ball of neutrons roughly 20 to 30 kilometers across. Over the following minutes and hours, it cools by emitting more neutrinos, contracting slightly, and settling into its final configuration. This is a neutron star, one of the most extreme objects in the universe, and we'll come back to what makes neutron stars and black holes so extraordinary. But first, there's another kind of supernova we need to understand, one that works through a completely different mechanism. The supernova has begun. From the outside, the star suddenly brightens. In a matter of hours or days, it goes from being a normal-looking star to one of the brightest objects in its galaxy. The light climbs rapidly, reaching a peak that can rival the combined output of every other star in the galaxy put together. Then it slowly fades over weeks and months, powered by the radioactive decay of nickel and cobalt in the expanding debris. The expanding shell of gas, glowing and turbulent, races outward into the surrounding interstellar medium. And at the center, hidden in the glare, sits the neutron star, or the newly formed black hole, the remnant of a core that lost its war with gravity, but, in losing, created one of the most spectacular events the universe has to offer. Everything we've talked about so far has been one type of supernova. A massive star, 8 or more times the mass of the Sun, fusing its way through element after element until it builds an iron core that collapses. That's a core collapse supernova. It's the death of a giant. But there's another kind of supernova that works through an entirely different mechanism. It doesn't involve a massive star at all. It doesn't involve iron. It doesn't involve a collapsing core. In fact, the star that triggers this explosion is already dead. It died long ago, quietly, without fanfare. It's a stellar corpse, a white dwarf. And what happens to this white dwarf, under exactly the right circumstances, produces an explosion so powerful and so consistent that it changed our entire understanding of the universe. This is the Type 1a supernova, and it's one of the most important phenomena in all of modern cosmology. To understand a Type 1a supernova, you first need to understand what a white dwarf is. And to understand that, you need to know what happens when a star like our Sun dies. Not a massive star, Not a blue supergiant, just a regular, ordinary star. The kind that makes up the vast majority of stars in the galaxy. Our Sun has been fusing hydrogen into helium in its core for about 4.5 billion years. It will continue to do so for roughly another 5 billion years. When the hydrogen in the core is finally exhausted, the core will contract and heat up, igniting hydrogen fusion in a shell around the core. The outer layers of the Sun will swell enormously, expanding outward until the Sun becomes a red giant, large enough to engulf Mercury, Venus, and possibly Earth. During this red giant phase, the core will eventually get hot enough to fuse helium into carbon and oxygen through the triple alpha process. But here's the crucial difference between a star like the Sun and a massive star. The Sun isn't heavy enough to go further. After helium burning, the core will be made of carbon and oxygen. But the Sun's core will never reach the 600 million degrees required to ignite carbon fusion. It simply doesn't have enough mass to generate the necessary gravitational compression. The core will contract, but it won't get hot enough for the next stage. Instead, the Sun will shed its outer layers in a series of thermal pulses, creating a beautiful expanding shell of gas called a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers thought these round glowing shells looked like the disks of planets through their telescopes, and the name stuck. What's left behind after the outer layers are expelled is the exposed core. A ball of carbon and oxygen, roughly the size of Earth, but containing roughly half of the Sun's original mass. This is a white dwarf. A white dwarf is one of the strangest objects in the universe. It's incredibly dense, a good fraction of the Sun's mass compressed into a sphere the size of Earth. The density of a typical white dwarf is around 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5.5 tons on Earth. That's roughly the weight of an elephant packed into a volume smaller than a dice. White dwarfs are hot when they first form, with surface temperatures that can exceed 100,000 degrees. But they have no internal energy source. No fusion is occurring inside them. They're not generating heat. They're simply radiating away the thermal energy they accumulated during the star's lifetime. Over billions and eventually trillions of years, a white dwarf slowly cools, growing dimmer and dimmer. Eventually, after an unimaginably long time, it will cool to the temperature of the surrounding space, becoming a cold, dark object called a black dwarf. But the universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs, those that formed from the very first generations of stars billions of years ago, are still too warm to have faded completely. What keeps a white dwarf from collapsing further under its own gravity? It's not fusion, because there is no fusion. It's electron degeneracy pressure, the same quantum mechanical force we encountered earlier in the iron core of a massive star. The electrons are packed so tightly that the Pauli exclusion principle prevents them from being squeezed any further. But here's what makes this crucial for white dwarfs specifically. Unlike the thermal pressure inside a living star, electron degeneracy pressure doesn't depend on temperature. It depends only on density. This means it doesn't matter how hot or cold the white dwarf gets. The pressure holding it up remains the same regardless. A white dwarf can cool for trillions of years, radiating away every last trace of its original heat, and the pressure supporting it against gravity never diminishes. The fire went out long ago, but the quantum mechanical scaffolding remains. This is why white dwarfs can exist essentially forever. slowly fading but never collapsing, at least not on their own. But as Subrahmanyan Chandrasekhar showed in 1930, electron degeneracy pressure has a maximum. There's only so much weight it can support. That maximum is the Chandrasekhar limit, approximately 1.4 solar masses. If a white dwarf somehow gains enough mass to approach or exceed this limit, electron degeneracy pressure can no longer hold it up. The consequences are catastrophic. Now, how would a white dwarf gain mass? It's a dead star. It's not growing. It's not accumulating material on its own. Left alone in the void of space, a white dwarf will simply cool forever. It will never explode. It will never do anything dramatic. It will just sit there, slowly fading. But most stars are not alone. More than half of all stars in the galaxy exist in binary systems. Two stars orbiting each other, bound together by gravity. And this changes everything. Consider a binary system where one star is a white dwarf and the other is a normal star, perhaps a red giant or a main sequence star that's beginning to expand. As the companion star evolves and swells, its outer layers can extend beyond its Roche lobe, the region of space where material is gravitationally bound to that star. Once the companion's atmosphere spills past this boundary, gravity from the white dwarf captures it. Material begins to flow from the companion onto the white dwarf. This process is called mass accretion, and it's one of the most important phenomena in astrophysics. The accreted material doesn't fall directly onto the white dwarf's surface. Because the material has angular momentum from the orbital motion of the binary system, it spirals inward, forming a swirling disk of gas around the white dwarf. This is called an accretion disk. The material in the disk gradually loses energy through friction and viscosity, spiraling closer and closer to the white dwarf until it eventually settles onto the surface. The accretion disk can be extremely hot, especially in the inner regions close to the white dwarf. Friction heats the gas to millions of degrees, causing it to glow brightly in ultraviolet and even X-ray light. Many of these accreting white dwarf systems are observed as cataclysmic variable stars, showing dramatic fluctuations in brightness as the accretion rate varies. As material accumulates on the white dwarf's surface, the white dwarf grows heavier. Gram by gram, kilogram by kilogram, year by year, century by century, the mass of the white dwarf increases. And as it increases, the gravitational compression on the interior grows stronger. The density and temperature at the center of the white dwarf rise. The white dwarf is being slowly, steadily pushed toward the Chandrasekhar limit. Now, what happens as the white dwarf approaches that limit depends on the specifics. But in the classic scenario, here's what occurs. As the white dwarf's mass approaches 1.4 solar masses, the density and temperature at the center reach a critical threshold. Remember, the white dwarf is made primarily of carbon and oxygen. These are fusible elements. Carbon can fuse into heavier elements if the temperature and density are high enough. And as the white dwarf is compressed closer and closer to the Chandrasekhar limit, the conditions at the center eventually become extreme enough for carbon fusion to ignite. But this isn't like carbon fusion in a massive star's core. In a massive star, carbon burning occurs under conditions of hydrostatic equilibrium. The star adjusts. If fusion produces more energy, the core expands slightly, cooling down and slowing the reaction rate. If fusion produces less energy, the core contracts, heating up and accelerating the reaction. There's a natural thermostat, a feedback mechanism that keeps things stable. In a white dwarf, there is no such thermostat. The white dwarf is supported by electron degeneracy pressure, which doesn't depend on temperature. When carbon fusion ignites and releases energy, the temperature rises, but the white dwarf doesn't expand to compensate. Degeneracy pressure keeps the material at the same density regardless of the temperature. So the temperature increases, but the density stays the same. A higher temperature means the fusion reactions proceed faster, which releases more energy, which raises the temperature further, which accelerates the reactions even more. This is a runaway thermonuclear reaction, a chain reaction with no off switch. Once carbon fusion ignites in the core of a white dwarf under degenerate conditions, there is nothing to stop it. The reaction rate doubles, then doubles again, then doubles again, escalating exponentially. Within seconds, the temperature raises to billions of degrees. The fusion burns outward through the white dwarf like a flame through dry paper, consuming carbon and oxygen and converting them into heavier elements, primarily silicon, sulfur, and ultimately nickel-56 and iron. The energy released is colossal. Within about 2 to 3 seconds, the entire white dwarf is consumed by fusion. Every gram of carbon and oxygen is burned. And unlike a core collapse supernova, where the outer layers are expelled while a dense remnant remains at the center, a Type 1a supernova leaves nothing behind. The entire white dwarf is obliterated. There is no neutron star. There is no black hole. There is no remnant of any kind. The white dwarf is completely destroyed, blown apart by the thermonuclear detonation. Every atom of carbon and oxygen that made up the star is converted into heavier elements, primarily nickel-56, and hurled into space. The explosion releases roughly 1 to 2 times 10 to the 51 ergs of kinetic energy. That's comparable to the kinetic energy of a core collapse supernova. But in terms of the energy that goes into visible light, a Type 1a supernova is actually brighter. The expanding debris contains a large amount of nickel-56, typically about 6/10 to 8/10 of a solar mass worth. As this nickel decays radioactively into cobalt and then into iron, it powers the supernova's light curve, keeping it brilliantly luminous for weeks. At peak brightness, a Type 1a supernova can reach an absolute magnitude of about -19.3, making it one of the most luminous events in the universe. For a few weeks, it can outshine its entire host galaxy. Now, the picture I just described, a white dwarf accreting material from a companion star until it approaches the Chandrasekhar limit and ignites, is called the single degenerate scenario. One degenerate object, the white dwarf, and one normal star. It was the traditional model for Type 1a supernovae, and it's still considered viable. But over the past few decades, astronomers have increasingly recognized that there might be another path to the same result. This is called the double degenerate scenario. In the double degenerate model, you don't have a white dwarf accreting from a normal companion. Instead, you have 2 white dwarfs orbiting each other. Both are dead stars. Both are compact, dense, and slowly spiraling toward each other. The reason they spiral inward is gravitational wave emission. Einstein's theory of general relativity predicts that 2 massive objects orbiting each other will emit gravitational waves, ripples in the fabric of space-time. These waves carry energy away from the system, causing the orbit to slowly shrink. Over millions or billions of years, the 2 white dwarfs spiral closer and closer until they finally merge. When 2 white dwarfs merge, The combined mass can exceed the Chandrasekhar limit. The merger is violent. One white dwarf, typically the less massive one, is tidally disrupted, torn apart by the gravity of the more massive one. The disrupted material wraps around the surviving white dwarf, rapidly increasing its mass and compressing its core. The conditions for runaway carbon fusion are met, and the thermonuclear detonation occurs. The result is the same: a complete destruction of the merged object, no remnant left behind. An explosion that produces roughly 6/10 to 8/10 of a solar mass of nickel-56, powering a brilliant supernova. The double degenerate scenario has gained significant support in recent years. Astronomers have searched for surviving companion stars near the sites of known Type 1a supernovae, and have often found nothing. If the single degenerate model were always correct, you'd expect to find a traumatized but surviving companion star near every Type 1a remnant, a star that had its outer layers stripped away and was blasted by the supernova shockwave. The absence of such companions in many cases suggests that at least some Type 1a supernovae come from double white dwarf mergers, where there's no companion to survive. In reality, both pathways probably occur. Some Type 1a supernovae likely come from the single degenerate channel, where a white dwarf accretes from a normal companion. Others likely come from the double degenerate channel, where two white dwarfs merge. The relative frequency of each pathway is still debated, and it's one of the active areas of research in supernova science. There are also variations on these themes that complicate the picture further. In some models, a Type 1a supernova can occur even when the white dwarf hasn't quite reached the Chandrasekhar limit. These are called sub-Chandrasekhar models. In one version, helium accreted from a companion accumulates on the surface of the white dwarf and detonates. The detonation of the helium shells sends a shock wave inward that compresses the carbon-oxygen core, triggering a secondary detonation in the core itself. This double detonation can destroy the white dwarf even if its total mass is below 1.4 solar masses. This model could explain why some Type 1a supernovae appear slightly less luminous than the classical Chandrasekhar mass explosions. It also helps explain the diversity observed among Type 1 as supernovae, because the total mass of the white dwarf at the time of explosion can vary, leading to different amounts of nickel-56 production and different peak brightnesses. Now, let's talk about why Type 1a supernovae matter so much to our understanding of the universe. Because beyond being spectacular explosions, they turned out to be one of the most powerful tools in all of cosmology. The key property of Type 1a supernovae is their consistency. Because the explosion always involves the thermonuclear detonation of roughly the same amount of material, around 1.4 solar masses of carbon and oxygen in the Chandrasekhar mass models, the explosion produces roughly the same amount of energy and roughly the same amount of nickel-56 every time. This means every Type 1a supernova has roughly the same peak luminosity. Not exactly the same. There's some variation, but the variation is predictable. Astronomers discovered in the early 1990s that brighter Type 1a supernovae fade more slowly, while dimmer ones fade more quickly. This relationship, called the Phillips relation after astronomer Mark Phillips, who quantified it in 1993, allows astronomers to calibrate each individual Type 1a supernova. By measuring how quickly the supernova's light fades, you can determine how intrinsically bright it was. And once you know how intrinsically bright it was, you can compare that to how bright it appears in your telescope. The difference between intrinsic brightness and apparent brightness tells you how far away the supernova is. This is the inverse square law of light. An object twice as far away appears 4 times dimmer, 3 times as far, 9 times dimmer. So by measuring the apparent brightness and knowing the intrinsic brightness, you can calculate the distance. This makes type 1a supernovae what astronomers call standard candles. Not perfectly standard, more like standardizable candles. But the principle is the same. You observe a type 1a supernova in a distant galaxy. You measure its light curve, how it brightens and fades. You use the Phillips relation to determine its intrinsic luminosity. You compare that to its apparent brightness, and you calculate the distance to its host galaxy. This works out to incredibly large distances because type 1a supernovae are so bright. They can be seen billions of light years away. No other distance indicator works reliably at such enormous scales. Cepheid variable stars, which are another type of standard candle, can only be observed out to about 100 million light years. Beyond that, they're too faint. But type 1a supernovae can be observed at distances of several billion light years, allowing us to measure the expansion of the universe across a significant fraction of cosmic history. In the late 1990s, 2 teams of astronomers set out to use type 1a supernovae to measure how the expansion of the universe was changing over time. Everyone expected that the expansion would be slowing down. After the Big Bang, the universe has been expanding, but gravity, the attraction between all the matter in the universe, should be pulling everything back together, decelerating the expansion. The question was how fast this deceleration was occurring. Was the universe expanding slowly enough that gravity would eventually halt the expansion and pull everything back together in a big crunch? Or was it expanding fast enough that the expansion would continue forever, gradually slowing but never stopping? The 2 teams were the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They observed dozens of Type 1a supernovae in distant galaxies, measured their distances, and compared those distances to the redshift of their host galaxies. What they found in 1998 shocked the world. The distant supernovae were dimmer than expected. Not brighter, which would have indicated a decelerating universe. Dimmer. This meant the supernova were farther away than expected. And the only explanation was that the expansion of the universe isn't slowing down at all. It's speeding up. The universe is accelerating in its expansion. This was one of the most surprising discoveries in the history of science. For decades, cosmologists had assumed the expansion was decelerating. That gravity was gradually slowing things down. Instead, something was pushing the universe apart faster and faster. Something was overcoming gravity on the larger scales. Something invisible, filling all of space, exerting a repulsive force that increases as the universe grows larger. This mysterious something was given the name dark energy, and despite more than 2 decades of research, we still don't know what it is. We know it constitutes about 68% of the total energy content of the universe. We know it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know it's been dominating the dynamics of the universe for roughly the last 5 billion years, causing the expansion to accelerate. But we don't know its nature. It could be a property of space itself, what physicists call the cosmological constant, a term Einstein originally introduced into his equations of general relativity and later called his greatest blunder. It could be a new kind of energy field that fills all of space. Or it could be something else entirely, something we haven't thought of yet. The discovery of dark energy through Type 1A supernovae earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. And it fundamentally changed our picture of the universe. Before this discovery, we thought the universe's fate was determined by the tug of war between the initial expansion from the Big Bang and the gravitational attraction of all the matter in the universe. After this discovery, we realized there's a third player, dark energy, and it appears to be winning. If dark energy continues as it has, the expansion of the universe will accelerate forever. Distant galaxies will recede from us faster and faster until they cross beyond our cosmic horizon, disappearing from view permanently. The observable universe will shrink. Billions of years from now, future astronomers will look out and see nothing but their own galaxy, isolated in a vast and empty void. The rest of the universe will have been carried away by expansion, forever beyond reach. All of this revolution in our understanding of the cosmos, came from observing the deaths of white dwarfs. Small, dense, dead stars that happen to have companions feeding them material. The consistency of their explosions, the predictability of their light curves, the fact that they could be seen across billions of light years, these properties made them the perfect tool for measuring cosmic distances. And that tool revealed that the universe is not what we thought it was. Let's step back now and clearly distinguish between the two main types of supernovae, because while both are called supernovae, they are fundamentally different events that just happen to produce similar amounts of energy and similar peak brightnesses. A core collapse supernova happens to a massive star, one that is still alive and actively fusing elements. The explosion is triggered by the failure of the core to sustain itself against gravity after running out of fusible fuel. The mechanism involves gravitational collapse, neutron degeneracy, core bounce, neutrino heating, and the revival of a stalled shockwave. A dense remnant, either a neutron star or a black hole, is left behind. The explosion expels several solar masses of material, including a mix of elements from hydrogen all the way up to iron and beyond. Core collapse supernovae occur in regions of active star formation because massive stars live short lives and die near where they were born. You find them in the spiral arms of galaxies, in regions rich with gas and young stars. A Type 1. A supernova happens to a white dwarf, a dead star that stopped fusing long ago. The explosion is triggered by runaway thermonuclear fusion, ignited either by accretion from a companion star or by a merger with another white dwarf. The mechanism is purely thermonuclear. There's no gravitational collapse. There's no neutron star formed. There's no core bounce. The entire white dwarf is consumed and destroyed. Nothing remains. The debris is almost entirely composed of heavy elements, primarily iron group elements, because the entire white dwarf was fused during the explosion. Type 1A supernovae can occur anywhere, not just in star-forming regions, because white dwarfs are old objects. They're the remnants of stars that died billions of years ago. You can find Type 1A supernovae in elliptical galaxies that have no ongoing star formation, something that never happens with core collapse supernovae. These differences are fundamental. The two types share a name: supernova, because from a distance they look somewhat similar. Both produce brilliant explosions visible across galactic distances. Both release enormous amounts of energy. Both scatter heavy elements into space. But the physics underlying them is completely different. One is a gravitational catastrophe. The other is a thermonuclear bomb. One leaves a remnant, the other leaves nothing. One requires a young, massive, living star. The other requires an old, dead, compact corpse. Understanding this distinction is crucial because it tells us something deep about the universe. It tells us that stellar death comes in many forms. That destruction can be triggered by different mechanisms under different circumstances. That the universe has multiple pathways for creating the conditions necessary for stars to explode. And that both types of explosions play essential roles in the cosmic cycle of matter, forging heavy elements and scattering them into space, seeding the next generation of stars and planets with the raw materials for complexity and, ultimately, for life. Both types of supernovae produce iron. In core collapse supernovae, iron is produced during explosive silicon burning, as the shock wave passes through the star's outer layers. In Type 1a supernovae, iron is the final product of the complete thermonuclear burning of the entire white dwarf. In fact, Type 1a supernovae are thought to be the dominant source of iron in the universe. Most of the iron in your blood, in the steel in buildings, in the core of the Earth, was probably produced in Type 1a supernovae billions of years ago. The iron was forged in the detonation of a white dwarf, ejected into space, mixed with other gas and dust, incorporated into a new cloud of material that eventually collapsed to form the sun and the planets. And now that iron is inside you, part of the hemoglobin molecules that carry oxygen in your blood, every heartbeat pumps iron through your body that was once inside a white dwarf star that detonated billions of years before the Earth existed. Type 1. As supernovae are also important for another reason that's often overlooked. They produce the majority of the universe's silicon, sulfur, and calcium. These elements, formed during the intermediate stages of the thermonuclear burning, are ejected into space along with the iron. Silicon is the second most abundant element in Earth's crust. Calcium is the mineral that makes up your bones and teeth. These elements exist on Earth because white dwarfs exploded in the distant past and scattered their ashes across the galaxy. The white dwarf that produced the elements in your body no longer exists. It was completely destroyed in the explosion. There's no remnant to visit. No neutron star marking its grave. No black hole lurking where it once was. Just an expanding cloud of debris that eventually mixed with the interstellar medium and became part of the raw material for new stars and planets. The white dwarf gave everything it had. Every atom, every particle. It held nothing back. And from that total destruction, new worlds were born. That's the story of the Type 1a supernova. A dead star, resurrected briefly by material stolen from a companion or by a violent merger with another dead star. Pushed past the limits of quantum mechanical pressure. Consumed by a thermonuclear fire that cannot be contained. And obliterated so completely that nothing remains except the elements it forged in its final moments. It's a different kind of death than the core collapse supernova. Quieter in some ways, more total in others, but equally important for the universe and for us. The explosion is over. The shock wave has torn through the star and launched its outer layers into space at tens of thousands of kilometers per second. The brilliant flash of light is climbing toward its peak, and for a few weeks this single dying star will outshine hundreds of billions of living ones. But what about the center? What's left behind in the place where the star's core used to be? Because when a core collapse supernova happens, the explosion doesn't destroy everything. The outer layers are ejected, yes, but the inner core, the part that collapsed and bounced, the part that launched the shockwave in the first place, that's still there. And what it becomes is one of the most extraordinary objects in the entire universe. If the original star was between roughly 8 and about 20 to 25 solar masses, the remnant left behind is a neutron star. This is the compressed core that reached nuclear density during the collapse and bounced. It's now a ball of almost pure neutrons, roughly 20 to 30 kilometers across. Think about that for a moment. An object containing between 1.4 and about 2 solar masses, more mass than the entire sun, compressed into a sphere about the diameter of a mid-sized city. If you placed a neutron star in the center of London or New York, its edge would barely extend past the suburbs, and yet it would contain more mass than the entire sun. The density of a neutron star is almost beyond language. At its center, the density reaches somewhere around 1 billion tons per cubic centimeter. A single sugar cube of neutron star material would weigh roughly 1 billion tons. That's more than the combined weight of every human being who has ever lived, packed into a volume you could hold between your fingers. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh about 6 billion tons, the weight of roughly a cubic kilometer of rock, compressed into a space smaller than your thumb. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. If you somehow found yourself standing on a neutron star, which is of course impossible for many reasons, the gravitational force would crush you into a layer of atoms thinner than a sheet of paper in less than a microsecond. A marshmallow dropped from a height of 1 meter above the surface would hit with the force of a nuclear weapon. The physics at the surface of a neutron star operates in a regime so extreme that it makes the interior of a normal star seem gentle by comparison. Neutron stars are also incredibly hot when they're first born. The proto-neutron star left behind by the supernova has a temperature of around 100 billion degrees in its core. Over the following minutes and hours, it cools rapidly by emitting neutrinos. Over the following years and centuries, it continues to cool, radiating heat from its surface. Even thousands of years after formation, a neutron star's surface temperature can still be around 1 million degrees, glowing brightly in X-rays. Neutron stars cool slowly because they have enormous thermal reservoir. The heat stored at their incredibly dense interiors takes a long time to radiate away. But perhaps the most remarkable property of neutron stars is their rotation. When the core of a massive star collapses from the size of Earth to the size of a city, conservation of angular momentum causes it to spin up dramatically. Think of a figure skater pulling their arms in during a spin. As the arms come in, the rotation speed increases. The same principle applies to the collapsing core. The original core might have been rotating once every few hours or days. After the collapse compresses it by a factor of hundreds of thousands in radius, it can be rotating many times per second. Some newly formed neutron stars spin at rates of dozens or even hundreds of rotations per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins at 716 times per second. That means its surface at the equator is moving at roughly 24% of the speed of light, almost a quarter of the fastest speed possible in the universe. And this is a solid object, not a gas or a plasma. A solid sphere the mass of the Sun, spinning 716 times every single second. Neutron stars also have extraordinarily powerful magnetic fields. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. The most extreme neutron stars, called magnetars, have magnetic fields that can reach 1 quadrillion times Earth's magnetic field strength. These fields are so intense that they would distort the shapes of atoms at a distance of 1,000 kilometers from the star. They can affect the propagation of light itself, bending and splitting photons through an effect called vacuum birefringence, which was predicted by quantum electrodynamics and has recently been observed in the vicinity of neutron stars. The combination of rapid rotation and powerful magnetic fields produces one of the most iconic phenomena in astrophysics: pulsars. A pulsar is simply a neutron star whose magnetic poles are not aligned with its rotation axis. The magnetic field channels radiation, mostly radio waves, but sometimes X-rays or even visible light, into two beams that emerge from the magnetic poles. As the neutron star rotates, these beams sweep through space like the beams of a lighthouse. If one of those beams happens to sweep across Earth during each rotation, we detect a regular pulse of radio waves. The timing of these pulses is extraordinarily precise. Some pulsars are as accurate as the best atomic clocks on Earth. They tick with a regularity that's almost eerie in its precision, each pulse arriving at exactly the predicted time, millisecond after millisecond, year after year. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University. She noticed a regular pulsing signal in her radio telescope data, arriving every 1.337 seconds. The signal was so regular that for a brief time, the team considered the possibility that it might be an artificial signal from an extraterrestrial civilization. They even nicknamed the source LGM1, standing for Little Green Men. But when a second and then a third pulsing source were found in completely different parts of the sky, the extraterrestrial hypothesis was abandoned. It seemed unlikely that multiple alien civilizations in different locations would all be sending signals with the same characteristics. The explanation had to be natural, and it was. These were rapidly rotating neutron stars, the collapsed cores of massive stars that had died in supernova explosions. Today, astronomers have discovered over 3,400 pulsars. They've become invaluable tools for studying physics. The extreme conditions inside and around neutron stars allow us to test theories of gravity, nuclear physics, and electrodynamics in regimes that we could never recreate in a laboratory on Earth. Binary pulsar systems, where a pulsar orbits another neutron star or a white dwarf, have provided some of the most precise confirmations of Einstein's general theory of relativity. The orbital decay of the Hulse-Taylor binary pulsar, discovered in 1974, matched the predictions of general relativity for energy loss through gravitational wave emission so precisely that it provided indirect proof of gravitational waves decades before they were directly detected in 2015. But not all core collapse supernovae leave behind neutron stars. If the progenitor star is massive enough, roughly above 25 solar masses, though the exact threshold is uncertain and depends on factors like metallicity and rotation, The remnant core is too massive for even neutron degeneracy pressure to support. Just as electron degeneracy pressure has a maximum mass it can support, the Chandrasekhar limit of 1.4 solar masses, neutron degeneracy pressure also has a maximum. This is called the Tolman-Oppenheimer-Volkoff limit, and it's somewhere between 2 and 3 solar masses, though the exact value is still debated because it depends on the equation of state of nuclear matter at extreme densities, which we don't fully understand. If the remnant core exceeds this limit, nothing can stop the collapse. No known force in physics can provide enough outward pressure to counteract gravity at these densities. The core continues to collapse past neutron star density, past any density we have a name for, and forms a black hole. A region of space where gravity is so intense that nothing, not matter, not light, not information of any kind, can escape once it crosses the event horizon. A stellar mass black hole formed from a supernova typically has a mass between about 3 and 20 solar masses. The event horizon, the boundary of no return, has a radius of roughly 9 to 60 kilometers for black holes in this mass range. That's comparable to or smaller than a neutron star. All that mass compressed into a region of space not much larger than a city. The formation of a black hole during a supernova can happen in different ways. In some cases, the initial collapse and bounce produce a neutron star, but material falling back onto the neutron star after the explosion adds enough mass to push it over the Tolman-Oppenheimer-Volkoff limit. The neutron star collapses into a black hole, sometimes within seconds of its formation. In other cases, the collapse may be so energetic and the progenitor so massive that the shock wave fails entirely. The stalled shock is never revived. No explosion occurs. The entire star simply collapses into a black hole. This is called a failed supernova, and astronomers have found tentative evidence for these events. Stars that were observed one year and simply vanished the next, without any visible explosion. They didn't fade or dim, they simply disappeared. The entire star fell into a black hole it created and was gone. Whether the remnant is a neutron star or a black hole, the explosion itself has already done its work. The outer layers of the star have been hurled into space, and those expanding layers carry with them something profoundly important. Elements. Heavy elements. The raw materials for planets, for chemistry, for biology, for us. The expanding cloud of debris from a supernova is called a supernova remnant, and these remnants are among the most beautiful and scientifically important structures in the galaxy. The most famous example is the Crab Nebula, which is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. They recorded the appearance of a guest star, a star that appeared suddenly in the sky where none had been visible before. It was so bright that it was visible during the day for 23 consecutive days, and visible to the naked eye at night, for about 2 years. That guest star was a supernova, and what remains today, nearly 1,000 years later, is a cloud of glowing gas about 11 light years across, expanding at roughly 1,500 kilometers per second. At the center of the Crab Nebula sits a pulsar, spinning about 30 times per second. The energy from this pulsar, its radiation and its particle wind, illuminates the nebula from within, powering its eerie bluish glow. Cassiopeia A is another well-known supernova remnant, one of the youngest in the Milky Way. The light from this supernova reached Earth around 1680, though there are no confirmed historical observations of it. The remnant was discovered in 1947 as one of the brightest radio sources in the sky. It's about 10 light years across and is still expanding at speeds of up to 6,000 kilometers per second. Deep inside it, astronomers have detected a compact object that is likely a neutron star, though its properties are unusual and still being studied. The Vela supernova remnant is much older, about 11,000 years old, and has expanded to a diameter of roughly 100 light years. The Vela pulsar at its center spins about 11 times per second. These remnants show us the aftermath of supernovae on different timescales, from young and compact to old and diffuse. As a remnant expands, it sweeps up interstellar gas, creating a shock wave that heats the surrounding medium to millions of degrees. This shock wave compresses the interstellar gas, and in doing so, can trigger the formation of new stars. Supernovae don't just destroy, they also create. The shock waves from supernova remnants are thought to be one of the primary triggers for star formation in the galaxy. As supernova explodes, its remnant expands, the shock wave compresses nearby gas clouds, and those compressed clouds collapse under their own gravity to form new stars. It's a cycle. Death feeding life, destruction seeding creation. But the most profound contribution of supernovae isn't the shock waves or the remnants. It's the elements. Supernovae are the primary source of most heavy elements in the universe. Without supernovae, the universe would contain almost nothing except hydrogen, helium, and trace amounts of lithium, the three lightest elements produced in the Big Bang. Everything else, every element from carbon to uranium, was forged inside stars and distributed into space by supernovae. Let me walk through what elements come from where, because this is one of the most important stories in all of science. It's the story of where the stuff that makes up everything around you actually came from. Hydrogen and helium were produced in the Big Bang, about 13.8 billion years ago. In the first few minutes after the universe began, the temperatures and densities were high enough for nuclear fusion to occur. Protons fused into deuterium, deuterium fused into helium-3, helium-3 fused into helium-4. By the time the universe had cooled enough for fusion to stop, about 20 minutes after the Big Bang, the composition of the universe was roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium. And that was it. No carbon, no oxygen, no iron, no silicon, nothing else. Just hydrogen, helium, and a tiny bit of lithium. If the universe had never formed stars, that's all there would ever be. But the universe did form stars, and stars are fusion reactors. They take those light elements and forge them into heavier ones. Hydrogen fuses into helium in the cores of all stars. Helium fuses into carbon and oxygen in the cores of stars, massive enough to reach the necessary temperatures. Carbon, neon, oxygen, and silicon fuse into progressively heavier elements in the cores of the most massive stars. This is called stellar nucleosynthesis, and it's the origin of most elements up to and including iron. But here's the critical point. Simply making these elements inside a star isn't enough. If the elements stay locked inside the star forever, they're useless. They can't form planets, they can't form molecules, they can't form life. The elements need to be released into space, and that's exactly what a supernova does. The explosion ejects the star's outer layers, carrying with them all the elements that were produced during the star's lifetime and during the explosion itself. Those elements mix with the interstellar medium, the thin gas that fills the space between stars. Over time, gravity causes some of this enriched gas to collapse into new clouds, and from those clouds, new stars and planets form. But supernovae do more than just release elements that the star already made. They also create new elements during the explosion itself. When the shock wave tears through the star's layers during a core collapse supernova, it heats the material to billions of degrees, triggering explosive nucleosynthesis. In these few seconds of extreme heat and pressure, elements are forged that the star could never have produced during its normal life. Silicon is fused into iron and nickel. Oxygen is fused into silicon and sulfur. Carbon is fused into neon and magnesium. These explosive reactions produce enormous quantities of heavy elements that are immediately ejected into space. And there's something even more remarkable. Elements heavier than iron, the elements from cobalt all the way up to uranium and beyond, cannot be produced by fusion at all. Fusion of elements heavier than iron consumes energy rather than releasing it. So how do these heavy elements get made? Through a process called neutron capture. There are two main ways this happens. In certain evolved stars called asymptotic giant branch stars, free neutrons are released gradually during late stages of stellar burning. These neutrons are captured by existing nuclei slowly enough that radioactive decay occurs between captures, building up heavier elements step by step. This is called the S process, for slow. But there's a faster, more violent version. During and immediately after a supernova explosion or a neutron star merger, the environment is flooded with enormous numbers of free neutrons. Nuclei capture these neutrons so rapidly that there's no time for decay between captures. This is called the R process, for rapid. The R process is particularly important because it's responsible for producing about half of all elements heavier than iron, including gold, platinum, and uranium. For decades, astronomers debated exactly where the RA process occurs. Core collapse supernovae were long considered the primary site, but recent evidence suggests that neutron star mergers, the collision and merger of two neutron stars in a binary system, may actually be the dominant source of R process elements. When two neutron stars collide, they eject material that is extremely rich in neutrons, providing the perfect conditions for rapid neutron capture. The detection of gravitational waves from a neutron star merger in 2017, along with the electromagnetic radiation from the resulting kilonova, confirmed that R process elements, including gold and platinum, were being produced in the merger debris. But core collapse supernovae likely contribute as well, particularly through neutrino-driven winds from the proto-neutron star in the seconds and minutes after the explosion. So the full picture of where the elements come from is complex. Hydrogen and helium from the Big Bang, carbon, oxygen, and elements up to iron from stellar nucleosynthesis and supernova explosions. Elements heavier than iron from neutron capture processes in supernovae and neutron star mergers. Every element in the periodic table has a specific origin, a specific cosmic process that created it. And supernovae are central to almost all of them. Now consider what this means for you personally. Your body contains roughly 65% oxygen by mass. That oxygen was forged by helium fusion and carbon fusion inside massive stars and released by supernova explosions. About 18% of your body is carbon, produced by the triple alpha process in stellar cores. About 10% is hydrogen, mostly from the Big Bang. About 3% is nitrogen, produced in the cores of intermediate mass stars during hydrogen burning via a process called the CNO cycle. The calcium in your bones was forged during explosive oxygen and silicon burning in supernova. The iron in your blood was produced during silicon burning in massive stars and during the thermonuclear detonation of white dwarfs. The phosphorus in your DNA was created during carbon and neon burning. The zinc, copper, and selenium that your body requires in trace amounts were produced by neutron capture processes. You are literally made of star stuff. Not metaphorically, not poetically, literally. The atoms in your body were forged in the interiors of stars that lived and died billions of years before the sun was born. Those stars exploded as supernovae, scattering their elements into space. Those elements drifted through the galaxy for millions of years, mixing with other gas and dust, until gravity gathered them into a new cloud that collapsed to form the sun and the planets about 4.6 billion years ago. The Earth formed from that enriched material, and eventually on this small rocky planet, those atoms arranged themselves into molecules, those molecules into cells, those cells into organisms, and those organisms into you. The iron in your hemoglobin was once inside the core of a massive star. The oxygen you just inhaled was once plasma in a stellar furnace burning at hundreds of millions of degrees. The calcium in your teeth was produced in a nuclear explosion more powerful than anything humans have ever built or ever could build. Every atom in your body has a history that stretches back billions of years through stellar lifetimes and supernova deaths and the cold darkness of interstellar space. This is what a supernova actually is, when you strip away the jargon and the equations and the technical details. It's the process by which the universe recycles itself. Stars are born from clouds of gas. They live for millions or billions of years, fusing light elements into heavy ones. They die, sometimes spectacularly, scattering those heavy elements back into space, and from the enriched material, new stars and planets form, carrying with them the legacy of every star that came before. Each generation of stars is richer in heavy elements than the last, because each generation inherits the products of all previous supernovae. The first stars of the universe, born from the pristine hydrogen and helium of the Big Bang, contain no heavy elements at all. They couldn't form rocky planets because there was no rock, no silicon, no iron, no carbon, just hydrogen and helium. When those first stars exploded as supernovae, they seeded the universe with its first heavy elements. The next generation of stars formed from gas that was slightly enriched. They could form a few rocky objects, though not many. When they exploded, they added more heavy elements. Generation after generation, the universe grew richer. By the time the sun formed, about 4.6 billion years ago, the gas from which it condensed contained about 2% heavy elements by mass. That might sound like a tiny amount, but it was enough. Enough to form rocky planets. Enough for complex chemistry. Enough for liquid water, organic molecules, and eventually life. Without supernovae, none of this would exist. Earth wouldn't exist. The elements that make it up wouldn't be floating freely in space. They'd be locked forever inside dead stars and neutron star cores, inaccessible and useless. Life wouldn't exist because the chemistry of life requires carbon, oxygen, nitrogen, phosphorus, sulfur, and dozens of other elements that are only available because stars exploded and scattered their contents across the galaxy. You wouldn't exist. A supernova is not just a star dying, it's the universe making itself more complex, more interesting. more capable of supporting the structures that eventually lead to planets, to chemistry, to biology, to consciousness. Every supernova that has ever occurred has contributed to the enrichment of the cosmos. Every supernova has added its elements to the galactic reservoir. And from that reservoir, everything you see around you was built. So when you look up at the night sky and see a star, understand what you're really seeing. You're seeing a nuclear furnace that is, right now, forging heavy elements in its core. Someday, perhaps millions of years from now, perhaps billions, that star will die. If it's massive enough, it will explode as a supernova. Its elements will be scattered across light years of space. And millions of years after that, some of those atoms might end up in a new planet. Maybe even a living creature on that planet. A creature that might, one day, look up at its own night sky and wonder where it all came from. The answer is supernovae. It always was. The stars had to die so that we could live. The universe destroys in order to create. And the most violent event a star can experience, the catastrophic collapse of its core and the nuclear detonation that tears it apart, is also the most generous. Because in dying, the star gives everything it has back to the universe. Every element it forged, every atom it built, all of it scattered freely into space for the next generation to use. The star holds nothing back. That's what actually happens during a supernova. A war between gravity and fusion reaches its final battle. Gravity wins, and the core collapses. The collapse triggers a rebound so violent that it tears the star apart. The debris, enriched with dozens of heavy elements, is flung into space. And from that debris, billions of years later, new worlds are born. Worlds like ours, made of stardust, held together by gravity, warmed by a star that will someday die the same way. Tonight, somewhere in the observable universe, a star is reaching the end of its silicon burning. An iron core is growing toward the Chandrasekhar limit. Electron degeneracy pressure is beginning to fail, and within hours, maybe minutes, that star will collapse. A flood of neutrinos will burst outward at nearly the speed of light. A shockwave will tear through the dying star, and a supernova will be born, briefly outshining its entire galaxy. We probably won't see it. It's probably too far away, too obscured by dust, too faint by the time its light reaches Earth. But it's happening. Right now. Somewhere out there, a star is dying. And in its death, it's creating the raw materials for everything that comes next. For new stars. For new planets. For new possibilities. Maybe, billions of years from now, for new life. The universe is a cycle of creation and destruction, and supernovae are the turning point where one becomes the other. They are the most violent, most energetic, most spectacular events that stars can experience. And they're also the most essential. Without them, the universe would be a simple, sterile place. Just hydrogen and helium forever. No planets, no chemistry, no life, no one to look up at the sky and wonder. But supernovae happened. They keep happening. And because of them, the universe is rich, complex, and alive. At least in one small corner of it. On one small planet. Where atoms forged in ancient explosions learn to think, to wonder, and to understand the very process that created them. That's what a supernova is. Not just the death of a star, but the birth of everything else. Thank you for joining me on this journey through one of the most extraordinary events in all of nature. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep dives into how the universe works. And the next time you look up at the stars, remember this. every heavy atom in your body was once inside a star that exploded. You are the universe's way of understanding itself, built from the ashes of stars that died so that you could live. Sleep well tonight, knowing that you are, quite literally, made of stardust. Good night.